All right. Aloha. I'm Harry Xu from first year PhD from UC Berkeley under Professor Trevor Darrell. It is my honor today to present our work end-to-end learning of driving models from large-scale dataset with my collaborator Yang Gao here. So first of all, I will give you an overview. I will introduce our project, our task, and our dataset. And Yang will more focus on mathematical formulation, models, and experiments. All right. Driving in the real world. People have attacked the very challenging task, autonomous driving, for decades. There were some complicated rule-based systems. But when the thing gets overly complex, we are trying to look for a method that is data-driven to get over the difficulties. So to be clearer, we are using deep learning to find an end-to-end trainable model to help with driving, mainly based on visual signals. But what is driving? Here is the definition. Given the current state of a vehicle, we want to predict all the plausible actions or egomotions of that vehicle. So in this case, alpha could be define the rotational motion, and S could be define the translational motion. So under such formulation, we can use egomotion instead of steering wheel or braking pedal to drive a car, which means we can learn a generic model. Just like a human driver who can drive different kind of cars. But if we want to have a generic model, we really need large set of driving experience. So let's look at the existing driving data set. Okay, I would say all the data sets are pretty good. They are good benchmark data sets for specific driving tasks. But for our task, I would say there are some of them are from virtual world, which has large domain gap to the real world. And some of them are from real world, but limited in a few things. And in terms of diversity, none of them are satisfactory. And most importantly, none of them is satisfactory in terms of length. So the largest one here is around 200 hours. So it's time to show off our Berkeley Deep Drive video dataset. I will first show a few samples of our dataset. The dataset is here. We collaborate with our partner Nexar to collect this dataset in a crowdsourced manner. So from the samples, we will see our dataset is real and is first-person view driving videos. And it is very diverse. It includes cities, highways, rainy days, nights and evenings, even construction zones. And still, most importantly, our dataset is incredibly large. It is larger than any existing driving dataset by 2 orders of magnitude. So you might be very interested in this dataset. Let me introduce more about our dataset. This is a comparison table among all the datasets. Our dataset, from the table, we can tell it is large, it is real, it is diverse. So some more information. So first of all, it's 30 frames per second. It's pretty high frame rate. Second is 720 progressive scan. It's very high temporal rate. And it's very high resolution. And it also includes IMU, a gyroscope, GPS, and magnetometer, which means it includes different kinds of auxiliary data. And one more thing. Our dataset would be publicly available to the whole community. You can find our dataset on our GitHub page. Okay, now my collaborator Yang will take over and introduce about our mathematical formulation and models. Let's welcome Yang.
Thanks, Henry. So here we propose our mathematical framework. First, we assume we have a world state S, which contains all the historical information we have about the history, including but not limited to visual information, other vehicle states, as well as other sensor modalities. And the driving model maps the world state S into a set of action scores. The action score simply measures the plausibility of each action under the current state. For example, the world state could be a single image of the current frame, and actions could either be discrete actions or continuous action. For example, for discrete action, it could simply be going forward, stopping or slow down, or turn left or turn right. And we use the ring here to denote the 4 action scores, where the greener part denotes the more plausible action. The action could also be a continuous action, such as the future angular velocity of the car. In this case, the driving model no longer outputs a set of action scores. Instead, it outputs a function which maps from a continuous variable to a set of action scores. Here, we use a semicircle to visualize the future angular velocity action scores. In this case, it's equally probable to either go left or go right. So this is our mathematical formulation. And we also propose the instantanation of an FCN-LSTM style of network to fit the driving model. First, each of the video frames is fit into the FCN network, and the output is the spatially rich features. And we feed the spatially rich features into the Lsdm to get the temporally fused features. And after we get the temporal fused features, we make the future egomotion prediction. The model can also optionally take in the previous trajectory of the car, as well as other sensor modalities, if available. We also propose the side segmentation loss, which takes in an image and go through the dilated FCN network and outputs a semantic segmentation of the current image. So the intuition behind this segmentation side loss is that it can guide the dilated FCN towards a better feature representation. So here we show some interesting results. First is the discrete action results. So the visualization is the same as before. The ring on the left with letter G in the center, which stands for ground truth, is the driver's action. And the right ring with the letter P in the center stands for prediction, which is our model's outputs. And the upper, lower, and left and right denotes going forward, stopping, and left and right turn. So as you can see in the first video, our model can learn the concept of the distance between ourselves and the car in the front. And it knows when to go ahead, and it knows when to stop. In this second case, we show that our model learns how to turn right. In the third case, the vehicle is traveling across an intersection when the traffic light turns from yellow to red suddenly, and our models can change our prediction sharply from being equal probability of going forward and stopping to a complete stop. Note that in our training data, we don't have any annotation about the traffic lights, but our model can learn that automatically. Next, about our continuous action prediction results. So here is our continuous action as future angular velocity. And the visualization is the same as before. The green denotes our model's prediction, and the blue one is the driver's action. So in the first video, the vehicle is traveling between a trolley lane and a sidewalk. It's obvious that the vehicle cannot turn right, because otherwise it will run onto the sidewalk. So our model only has single-sided prediction, which is consistent with the video. In the second case, the vehicle is traveling along a curvy road, and we can see that our model has the correct lane-following behavior. Besides the lane-following behavior, our model also has multi-modality outputs, which means when the car have multiple choices, and like all of them is viable, our model will output them all at once. To better understand what our model is doing, we further visualize the COM4 activations of the dilated FCN. So the left-hand side is the activation heat map, and the right side is the raw image. And in this first image, as you can clearly see, that our model focuses mostly on the lane markers as well as the traffic lights. And that partially explains why our model can learn to look at the traffic light without explicitly supervision. And in the second case, our model focuses on the bicyclist on the side. And in the third case, our model not only focuses on the traffic light, but also focuses on the car traveling in the front. although it's mostly focusing on the wheels instead of the whole body of the car. That's an artifact of the ConvNets. We also compare the privilege training results, which is the side segmentation loss, with a few baselines. So in this case, the car is stopped in a traffic jam, and the car in the front is stopping. So the true behavior should be stopping. And P1 through P3 are 3 methods, where P1 is a baseline with only image segmentation as input. And P2 is the method without any privilege training. And P3 is the full model with privilege training. And as you can see, only the privilege training results has the correct behavior. So in conclusion, we introduced a generic actuator-independent driving model that can drive multiple models and makes of the car. And we also curated a public large-scale datasets, which we can train driving model from. We also proposed a novel FCN-LSTM style of architecture, and also evaluate the usefulness of the privilege training paradigm in this scenario. Last but not least, we are the first to train a driving model on the scale on a dataset that has a scale of a human lifetime scale. So this chart compares our current Berkeley Deep Drive video dataset with how many hours a human can drive in their lifetime. We can see that they are on the same order. And in the future, we will collect a dataset that is 10 times larger than the dataset we have right now, since we think a dataset should cover the rare events that a human might not be able to see once in their lifetime. And this is pretty important for the safety of the autonomous driving. Another future work is to deploy our model on a real car. So this picture shows off the Berkeley Deep Drive car we are building right now. And it has the LiDAR and all the sensors. And yeah, that's all. Any questions?
We'll have time for questions. Any questions? There's a microphone over there.
Hi, very impressive talk and results. I'm just curious, you mentioned you already have data at night and under the rain and these kind of really challenging conditions. How does your model work when, in these cases?
So you are asking about whether our model works in the night or in the rain?
Exactly.
Okay, so we didn't show the results here, but actually our model works perfectly in the night. We have some visualizations, but it's on our poster. And in the rainy days, we don't have a lot of data. So, but I think if we have enough data, that will also work.
Thank you.
Yep.
Any other questions? Go ahead.
Yeah, very impressive work. I guess my question is, how does your model really learn to distinguish between ambiguous cases? For instance, in the image here, you have a turn where the car can basically either go straight or right. How do you know which one's the right one to do without future context, such as where the car should go? Yep, pretty good point. So we do not aim to predict a single plausible action. Rather, we aim to predict all the plausible actions. So our model is not a single component of the whole self-driving system. It serves as a middleware. So the top-level planner will choose which action to actually perform. Cool. Thanks.
Thank you.
Okay, so let's thank the speakers again.